Hello, this is Joe Neville and welcome to VXLAN Explainer video 3. In this video, we're going to be looking at VXLAN packet forwarding. We're going to be defining the control plane and the data plane. We're going to be looking at data plane learning, its limitations and how it can be improved upon with BGP EVPN. Then I'm going to lab it up. We're going to look at the configs. And it wouldn't be a VXLAN Explainer video without some wireshark. So we're going to go deep, we're going to sniff some packets. Okay, that's it for the intro, let's get into it. Hello and welcome to this latest video in my VXLAN Explainer series. Now in this video, I'm going to be looking at VXLAN forwarding. And what I mean by that is the forwarding of traffic by VTEPs in a VXLAN network. And we'll be looking at what processes do VTEPs employ to ensure that they're sending traffic to the correct VTEP peer. First of all, we're going to go through the theory and then I'm going to lab it up at the end with packet captures and I'll show you live configuration. Now, if you've watched my previous videos, and if you haven't, please do, because this will make a lot more sense if you do, link on screen now. The scenarios that we've been using have been rather simple, which is on purpose. For example, here we've just got two VTEPs separated by this /30 underlay, and we've got a couple of customer side servers. If we look at the configuration on this VTEP, we have a VXLAN interface, source IP address. I'm going to use loopbacks for this. We've got a single VNI, we have the VLAN, so that VLAN is the customer side VLAN, which is then bound to the VNI, and we have a single VTEP peer, hence the name. And the decision-making process for this VTEP is that if customer traffic arrives on this port, it's either going to switch it locally if it knows about the MAC locally, or it's going to encapsulate it and send it to the VTEP peer. There is a third option that it could be dropped, but for our purposes, it's either switched locally or it's going to be encapsulated and sent across. So we only have one VTEP peer to send it to. Now, if we expand this out, now I've added in an extra VTEP and an extra Ubuntu server. So now on the customer side, we've got UB1, UB2, and UB3, and they sit in a customer side network, which is 172.18.1/24. And I've got .1 here, .2 and .3, and that customer network is separated by this layer 3 underlay, which I've also expanded so that it's now a /24, so it's 10.150.99, and the VTEPs sit on that, the VTEP 1 here, so it's a 6300-1, the VTEP IP address is 1.1.1.1, but on the underlay it's 10.150.99.1, and then we've got .2 and we've got .3. Also, a point of note is for illustrative purposes, I've simplified the MAC address so I'm not having to juggle long MAC addresses. I've just abbreviated it to a single letter. So UB1 is just, for our theory, is just MAC A, UB2 is MAC B, and UB3 is MAC C. Now, looking at the configuration on this VTEP, and I should say that everything that I do at the theory stage is going to be from the point of view of this VTEP. The traffic will be bi-directional, and so the processes are happening in a bi-directional way. But the way that I'm going to explain the theory is just from the point of view of the VTEP 1 here, this 1.1.1.1. I think that creates a stronger, clearer narrative as we step through the process. Okay, so here is the configuration. It's exactly the same as we saw with a single VTEP peer, but we now have two VTEP peers. But one of the important points that we need to discuss then is how, if customer traffic arrives on this port, how does this VTEP know which of the VTEPs to send the traffic to reach the correct destination, .2 here or .3 over here? Because in the configuration, there's no link between the customer side network, this 172.18.1/24. So we're going to do a packet walkthrough of what's happening here, what processes are involved. Now, here's the scenario then that we're going to use. Very simple. UB1 wants to ping UB2. Now, how does that happen? Okay, so let's step through it then. This is our packet walkthrough. First of all, UB1 pings UB2. So it knows its IP address, 172.18.1.2. Of course, to send the ping, you need the IP address. And remember, the customer side nodes, they know nothing about VXLAN. So they're just going to act in this scenario as standard IPv4 traffic forwarding. So UB1 pings UB2. But first of all, and we're starting from scratch here, we need to ARP for the MAC address that's associated with 172.18.1.2, of course. So an ARP is broadcast by UB1, that hits the VTEP, and the VTEP checks the destination. So that's we haven't encapsulated yet. It's checking the destination, which will be the inner MAC address, and that's broadcast. So it's not local because it's going to be broadcasted. So this VTEP knows that that's not going to be a MAC that's local here that it will switch. It's going to have to send it out to its VTEP peers. And to do that, it uses a process called head-end replication. Okay, so quick look at that then. So the head end is the sender, it's the transmitter. The tail is the receiver. So the traffic flows from head to tail. In this case, like I said, the point of view is always going to be this VTEP. This is our head. These are going to be our tails. So what we do, we use the head will replicate, and it will replicate to the VTEP peers. At this stage, we've got a broadcast, so we're just going to send that out to our two VTEP peers here. So what happens, we use head-end replication, and that means that a copy goes to this VTEP 1.1.1.2 and to 1.1.1.3. They will receive that and they will decapsulate it, and because it's the inner MAC is broadcast, they will send it onto their local LAN. And this is standard IPv4 at this stage. So UB3 doesn't know about 172.18.1.2. It will just discard that ARP. But UB2 will respond with its MAC address, and it will send it back on the local LAN, which will hit the VTEP. So the ARP reply will be encapsulated by the 6300-2, and it will hit the 6300-1 over here, which will decapsulate that packet. And what this VTEP will do is it will employ what's called source address learning. So it will record the VTEP source address that the packet came from, that being 1.1.1.2, this VTEP here, and it will look at the inner Ethernet header, which will include the source MAC address of UB2, that being in this example MAC-B, and it will record that using this process, source address learning. It will record it for future reference. It will record the VTEP IP and MAC binding. And you can see this on an Aruba AOSCX device in the show MAC address table. So here's an example of one from 6300-1. I've simplified it, of course, with the MAC address. Here we have the MAC, so MAC-B from UB2, and the port that it's learned on. So the port obviously is going to be VXLAN 1, but here's that vital information. It's the VTEP IP address next to it, 1.1.1.2 over here. You can also see that this is just standard L2 switching table because we've also got this other MAC here, which is A, which is UB1 on the local LAN, and that's learned on port 1/1/20, which is this port here. So VXLAN is using this L2 table to record the MAC and the VTEP IP address binding. 6300-1 will forward on the decapsulated ARP reply, which will hit UB1, and that will record the, just as standard IPv4 ARP, it will record the UB2 IP address to MAC binding after that successful ARP exchange. Okay, so that's just the first step of this process. What we're really trying to do, if you recall, is to send a successful ping. So now we move to that stage, now that UB1 has the MAC and the IP address of UB2. So UB1 will send an ICMP echo request to 172.18.1.2 with MAC address B, because remember, this is all just at L2. UB1 doesn't know anything about VXLAN or the L3 divide here. It thinks that it's just switching a packet to a local neighbor. So the ICMP echo request is sent. That's going to hit 6300-1, and when our VTEP goes to encapsulate the packet, it will refer to its MAC address table and it will see this binding. So it will know for MAC address B, which is the destination of this ICMP echo request, it will know now that that MAC address can be reached via this VTEP 1.1.1.2. Here we are. So that's where the binding comes in and the source address learning. So now 6300-1, it doesn't need to employ head-end replication. It doesn't have to send anything to all of its VTEP peers. So we don't have to send anything to 1.1.1.3 in this process. We can just encapsulate the packet and send it directly to 1.1.1.2. which is what 6300-1 will do. And 6300-2 will decapsulate that packet, send it on to UB2, which as part of the standard ICMP process, it will send an ICMP echo response back to UB1. That hits 6300-1. And that will get forwarded on after it's been decapsulated and sent to UB1, and that results in a successful ping. Now let's dive a little bit deeper into what's happening here with this source address learning. So let's have a closer look at the RFC. I've quoted this in every one of these videos, so you should be familiar with this by now. RFC 7348, and it talks about a control scheme, and it calls it data plane learning, and this is where the association of the VMs. Okay, so I should say that the RFC is written from the point of view that the customer servers are all VMs, that everything is virtualized. It can be a physical server. In our scenario, it's just the Ubuntu servers. So the association of the Ubuntu server's MAC address, so those MACs that I've abbreviated to A, B, and C, the association of those to the VTEP's IP address is discovered via source address learning. Okay, so that's what we've seen. The VTEPs are listening to the traffic as it's flowing, looking at the inner MAC address, which is the Ubuntu servers or the VMs in the RFC, and then saying, okay, which VTEP did that packet come from? Once I hear from a VTEP, I look at the inner MAC address and I record that in the MAC address table. That's what we've seen. But it calls it data plane learning. I think it's worth asking what's going on here. Why is it called data plane learning? And what are some of the problems with this? Because it's not the most efficient way to do these things. Data plane then. Now, this isn't a term specific to VXLAN. This is just a general networking term. It's also known as the forwarding plane, and it's the part of a layer 3 node, like a router or an L3 switch, which is concerned with the forwarding of the traffic. So the job of the data plane is to take in the traffic and process it as quickly and as efficiently as possible. Either it's going to be dropped or it's going to be sent out of the correct interface. It's all to do with getting that traffic to the right destination as quickly as possible. And when we mention the data plane, we should also introduce its sister term, which is the control plane. Now, the control plane is the part of the layer 3 nodes architecture, which is concerned about the view of the network. So this, in the control plane, this is what populates the routing table. So it's not concerned with just the forwarding of the traffic. It's about getting visibility of the network. The routing protocols work at the control plane. So here you can see we've got the job of the control plane is to view, I've got a very simple network here, but at the control plane, what we would be doing, the control plane of this device would be building the routing table via either static or it would be routing protocols that allow the device to know what's out there on the network. So it will have connected interfaces, but also here I'm using eBGP as well to find out about this one. So the control plane populates the routing table, and then when traffic arrives, it's the data plane which deals with forwarding the traffic to the correct destination. So we've got data plane and control plane. But what we were talking about is data plane learning. Now, the data plane is really about forwarding traffic. It's not so much about visibility on the network. So learning about the network at the data plane level is actually a really suboptimal way of doing it. It's quite inefficient. It doesn't scale. And one of the points is, as we were doing the packet walkthrough, at the start, the device didn't know anything about the VTEP and the MAC address. It has to broadcast. So it sends out broadcasts or it sends out unknown unicasts onto the network. It has to have active traffic to populate that MAC table. So we're kind of using a process there which does work, but isn't the most efficient. And if we're talking in terms of data plane and control plane, surely it would be better to use the control plane to get visibility of the network, to learn these VTEP to MAC address bindings, rather than using traffic flowing through the data plane. And so I've said it's suboptimal and inefficient. I'll give you an example of that. So let's have a look at some of the issues with this data plane learning. And for this, I've employed the power of emojis. Now, we've already run through this first part, but I think it is worth going over this so you can see where the issues lie in the full story. Now, what we have here is we've got a packet from MAC A that needs to go to MAC B. This first VTEP doesn't know about MAC B on the local LAN, so he thinks I better send it to my VTEP peers, send it off to my VTEP buddies. So using head-end replication, we now have these two copies which are sent to VTEP 2 and 3. Those packets are forwarded on. MAC C will discard that because it is addressed to MAC B. MAC B recognizes that's for itself, which hits VTEP 1, and VTEP 1 records that VTEP IP address to MAC binding for 1.1.1.2, and MAC B in its table down here, as we've seen. And then when a new packet arrives from MAC-B, the VTEP knows about the binding, and so it sends it straight to 1.1.1.2, send it straight to the correct VTEP. But then, what happens next? We have a packet for MAC-C, and our VTEP doesn't know about that, so we have to use head-end replication again. And then the VTEP is feeling pretty good about itself because it has entries for MAC-B and MAC-C, so we have C there going to 1.1.1.3 and B to .2. So we don't have to use head-end replication for these unicasts because they're known now. So that's more efficient at this stage, and data plane learning in action. And then 300 seconds later, and that 300 is the default timeout for that MAC address table with Aruba AOSCX. And then the VTEP hasn't heard from these MACs, and the MAC age timer has expired, so it scrubs clean the table. And then what happens? Well, of course, we get a packet for MAC-B. Our VTEP consults its MAC address table. It doesn't have an entry. So what are we going to do? Of course, we're going to rely on head-end replication again. So we're back to that inefficient stage where we're sending out these, what are essentially unknown unicasts. So how can this situation be improved? Well, you may say, well, I'll just up the timers, but that's not really solving the problem. It might slightly alleviate this one issue, but you certainly don't want to be playing around with what is essentially the basics of L2 switching on your network. You certainly don't want to get into a situation where your devices have L2 tables that are close to maximum because you've been tweaking the timers. And this is a VXLAN specific issue, so why not try to solve it with a VXLAN specific solution rather than tinkering with basics like L2 switching on your network? So if we have a look at the RFC for VXLAN, we see that it does suggest, this is a quote from it, it does suggest a control plane for the distribution of VTEP IP to MAC address. So this mapping information that we're previously learning via the data plane, let's use the control plane for this to give us a view of the network. And the option it offers up is one of a centralized authority directory-based lookup for the individual VTEPs with that distribution mapping information. So this is kind of like having a central brain that the VTEPs would all be speaking to, and they would push up their MACs, I guess. Is how it would work. This makes me think of the ideas of like a controller on an SDN network, the kind of ideas that were gaining in popularity around the time of the RFC was written in like 2014. So that's a centralized directory. But what's a more network engineer centric approach to distributing information around a network? How do we populate routing tables? Well, we do that with routing protocols, don't we? So what other ideas might we have to distribute this information? Could we distribute the VTEP IP to the MAC like we distribute IP route information? How would we do that? And I'm kind of eking this out because it's pretty obvious what we would use, isn't it? Anybody that knows networking knows that we just use BGP for pretty much everything nowadays. You know, it's our kind of go-to for this kind of exchange at the control plane. You know, it started off with IPv4 addresses, and it's V6, and it's multicast, then it's VPN v4, VPN v6. All kinds of data is being exchanged through the network using extensions to the BGP routing protocol. And that leads us on to BGP EVPN, and EVPN stands for Ethernet VPN. So this is a control plane that uses BGP to propagate the binding. So rather than IP addresses, rather than v4 or v6 addresses that are being propagated, what we propagate is the VTEP IP to the MAC address binding. So we don't have to use the data plane source address learning, which is inefficient. We can build a view of the network using this controller plane, which, and if you know anything about BGP, it's much more scalable. It's not going to time out like the issues that we've seen there with the data plane learning. So effectively, BGP EVPN VXLAN is not just one bound up solution. It's actually two different distinct parts. What we have is we have BGP EVPN for the control plane, sending those bindings through the network via BGP, and we have VXLAN for the encapsulation of the traffic, adding those 50 bytes to the header. So that's working at the data plane. And these two, this is, like I said, it's not just one solution. These can be decoupled. So this control plane doesn't need to use this data plane. What you can have, and in the RFC, there's an RFC 8365, which has got the snappy title of a network virtualization overlay solution using EVPN. It actually suggests different data planes. It doesn't just suggest VXLAN. You've got MVGRE, you've got Geneve, you've got MPLS over GRE. So we can have different encapsulation methods which will utilize the same control plane. Obviously, they'll utilize it in different ways, but there is a decoupling between the control plane and the data plane. It's like it's modular. So when you hear people talking about BGP EVPN, that's one thing, that's the control plane, and VXLAN, that's just the data plane. So hopefully I've shed some light on this pretty complex networking stack by just focusing on where VXLAN sits in this, where we have, it's just the data plane, okay? You can do source address learning as we've seen, but really the more efficient way is to plug in a control plane, to use BGP EVPN for that exchange of the bindings. But really that's another story that I'm going to go to in another video. So that's the future of this series. So VXLAN Explainer is going to turn into, it's going to morph into a wider explainer series about BGP EVPN. Okay, this is the narrative. We start with VXLAN, then we move on to fitting that into the BGP EVPN VXLAN stack to really understand what's going on there. And so that will be future videos. But for now, we're going to lab it up. I'm going to run that packet walkthrough so we can have a look at source address learning. So this data plane learning using VXLAN on my home lab here. Okay, so here's the lab and I've got a number of windows on screen. Let's run through them and explain what we're going to do here. Okay, so this down in the bottom right is, of course, a network diagram. This is the same as the packet walkthrough. I've got my 3 VTEPs, which are Aruba 6300s. Those are physical devices that are running in my home lab. They're connected together on this underlay network of 10, 150.99/24. And then I've got these 3 Ubuntu servers, so UB1, UB2, and UB3. Those are physical servers as well. And the scenario that we're going to run through is the same as the packet walkthrough, which is UB1 is going to ping UB2. We'll have a look at the config. I should say that I'm going to do everything from the point of view, just like I did in the walkthrough, from 6300-1. Because with data plane learning and bidirectional traffic, you've got that learning happening on the different devices at different times. We're just going to keep the narrative clean by focusing on this 6300-1 and UB1. So over here on the left, I've logged into UB1 where I'm going to do the ping, and I've got an SSH session to 6300-1. Now, when we do the ping, we'll be able to pick up the packets because I have mirrored this port here. This is 1/1/10 on 6300-1, and that's connected to my laptop, and the traffic is going to appear up here in Wireshark. I'm filtering on ARP and ICMP, the things that are important to us in this scenario. Okay, so let's have a look at the salient parts of the configuration on 6300-1. Now, first of all, I think, yeah, so we've got this interface here. This is the underlay connected interface. And there you can see it's 10.150.99.1, and that's in OSPF. Now, the reason for that is that I'm using for the VTEP IP addresses the loopbacks. The neighbors aren't going to know about the loopbacks. I need some way of advertising those to set up the VXLAN encapsulation and decapsulation. Rather than using statics, I'm just going to put them into OSPF area 0. So the underlay is running OSPF. If I scroll down, you'll see there's my VXLAN interface 1, the source address of 1.1.1.1, no shut, of course. I've just got a single VNI there tied to that VLAN 101, which is the customer side VLAN. And then I've got my 2 VTEP peers pointing to their loopbacks. If we look further up, actually, there's the loopback 0, 1.1.1.1/32, and I've put that into OSPF, of course. Below there, if you're interested in that mirroring, so mirror session 1, the source interface is that 1/1/10, that's enabled, and the destination is the port 1/1/23, which is connected to my laptop. And then finally at the bottom, we've got OSPF turned on. Okay, so a few checks to make sure that everything is up and running correctly. Let's have a look for our OSPF neighbors. Yep, I can see the 2 other VTEPs. Let's have a look at the routing table. Yes, so I've got the loopbacks in there. Now, if I do a ping to check that connectivity, that's successful. And now .3. Yeah, okay. So this should all work. Fingers crossed. And to ensure we have a clean exchange of traffic in our capture, I want to make sure that all the tables are reset. So let's have a look at -1's MAC address table. And as you can see, there's only one MAC known, and that is from my laptop. That's just some traffic that's coming in on the destination mirror port, so we don't need to worry about that. That's not in our traffic path. And on UB1, I want to make sure that I don't have an ARP entry, which I do not. I put the MAC addresses, actually, of the two servers under here for reference. Okay, so we are ready to go. If I start the capture, which I will do now. Okay, we're capturing. I'll do a ping count of 1, and I'll go 172.18.1.2. Send that, good, and I'll do a stop, and I will capture a show MAC address table. Okay, because that will time out if I take too long explaining this. Right, so what can we see here? Let's run through them. So here are the packets. Now, first of all, we have the ARP. I'll pull this down so we can, let's try to get all of this on screen. Okay, now from the bottom to the top. So this is the ARP request that is coming from UB1. So the MAC source is 2FC9A1. Okay, so going from inner to outer, we have the ARP request, then we have the inner Ethernet header, as you can see, 2FC9A1, that is UB1, and it's broadcast because UB1 did not have an entry for this IP address. So it sent an ARP request to the broadcast at layer 2. That's been encapsulated, and if we have a look at that, here's the VXLAN header, and that is in VNI 1. Yes, okay, so we only had one VNI. Next, we've got the UDP header, and we've got the outer IPv4 header, and have a look at that source there. So the source is the loopback for 6300-1, and it's going to 6300-2 there. But because the inner MAC is a broadcast, the 6300-1 will utilize head-end replication. So if we look at the next one, we see it's another ARP request from the same source. Now, the source will have only sent one. Remember, we're mirroring here. 6300-1 is employing head-end replication across the VXLAN network. So what we see is the source is 1.1.1.1 and the destination is 1.1.1.3, the other VTEP peer that 6300-1 knows about. If we look at the first one, it's to .2. If we look at the next one, it's to .3. And as we know from the packet walkthrough, what will happen is that this broadcast will be decapsulated on -2 and -3. It will hit UB3 and be rejected as per normal ARP. UB2 will pick it up and realize that it's destined for it, and it will send a response, which is what you see in the next packet there. So this is, if we have a look at the inner, going inner to outer again, this is an ARP reply that is coming from, so B959A6, B959A6, so it's coming from UB2. And it's going straight back to UB1 at this point. Of course, this is just standard ARP. Again, the VXLAN header, the VNI, UDP, and we have the source of 1.1.1.2 and the destination of 1.1.1.1. And once this packet travels across the network and hits 6300-1, 6300-1 will do data plane learning. This is what we've been talking about. So that's the show that I've captured here. You can see the MAC address, B959A6, that is UB2, that is known on VXLAN 1 with the VTEP IP address of 1.1.1.2. So that's data plane learning in action, and 6300-1 will have decapsulated that packet and sent it on to the destination MAC. So the ARP reply will hit UB1 and UB1 will populate its ARP table, which it has done here. So 172.18.1.2 has now registered the MAC address for UB2. There you go, B959A6, B959A6. Okay, excellent. So this is all working as normal. Now the next step, and this is, I should note that this isn't in keeping with what really should happen, but I guess it's because the table hasn't updated. This table hasn't updated quickly enough. So what you see is that when the ARP comes in and then the server sends the ping request, 6300-1 still does head-end replication. So we do see 2 of these echo requests come in. Let's have a look at the first one. So the inner, it's the ICMP message, of course. Then it's an inner IPv4 header with the source of 172.18.1.1 going to .2. You've got the VXLAN there. And then the outer is from 6300-1 using the VTEP IP address to 6300-2. And the next one along, so head-in replication is in action still. The destination is 1.1.1.3. And as I say, my assumption being that between ARP and ICMP happening on the Linux server, the device hasn't updated its table and has still performed head-in replication at this stage. But what we see then as the final packet in this exchange, we have the reply, and that is coming from UB2. So we go ICMP, the IPv4 with the source of 172.18.1.2, going back to UB1. That's been encapsulated, and the source is .2, and it's going to 1.1.1.1. That hit UB1, and that's why we got a successful ping for the first exchange. Okay, so let's have a look. Now that we've actually got the ARP entry in, if we clear off the MAC table there and run this again, so do a clear MAC address table, I think VLAN 101. Okay, so now we'll just have the echo request rather than the ARP. Okay, so let's run that ping again. I am capturing. Okay, so we'll stop that. And what we see is we've still got the 2 requests in there. So we don't need the ARP because the ARP's been populated at this side. This is just normal IPv4. It's not really VXLAN. But if we check this MAC table, so this is the important point, we do have an entry there for UB2's MAC address and the port. So subsequent pings should just go, yeah, as you see, we just have the single request. So 6300-1, when we do a second ping, it's not employing head-in replication at this stage. We know that if we want to get to this MAC address, which we pick up from the inner Ethernet header here, we send it directly to that VTEP. So data plane learning is in action. Let's do that again so you can see that. Okay, as you see, like each one of those is just a single that's going directly. So no traffic is going over to .3 at this stage. The request is just going directly to .2 because data plane learning is in action. Okay, but if we then clear this off, if this was to time out because we've got no active traffic, as mentioned, we'll do, okay, clear MAC address VLAN 101. Check that. Okay, so we don't have an entry. What's going to happen? I'll start that up. We do the ping, and there you are. The head-in replication is back because we didn't have an entry. Send it again. Only 1 request is sent. Send it again. A single request. Clear it off. Send another request. Yep, you get 2. 1 to .2 and 1 to .3. Okay, that's it for this video. Thank you so much for your support of the VXLAN Explainer series so far. Now I'm going to branch out from VXLAN and I'm going to start the BGP EVPN Explainer series using BGP EVPN as the control plane, of course, and VXLAN as the data plane. So please do look out for future videos. And just a quick word to say, these videos do take me a long time to make, so please bear with me. I'll be getting those out as soon as I can, okay? And that just leaves me to say, my name is Joe Neville. Thank you for watching and goodbye.